So we're going to look at the chi-square test. The chi-square test is a hypothesis test, but it's a special type hypothesis test. So as it says up here, the main use of the hypothesis test is to see if there's a relationship between two variables. When we first do the test, we don't say what we think the relationship is, but what will happen is after we do the test, if we do find a relationship, then we'll say what we think the relationship is. And this can be used for categorical or quantitative variables. It doesn't matter. If they're quantitative, we'll actually change it to categorical or change it to groups. That's kind of how it works. And again, like everything else, we're just assuming the only real assumptions we have random samples. The nice thing about the chi-square test is that H0, the null hypothesis, and HA, the alternative, don't change. We won't have to worry about different cases of the alternative as we did with the regular hypothesis test. The null hypothesis is there is no relationship between the two variables, whatever they are, which is the same thing as saying the two variables are independent. That's why you sometimes hear about the chi-square test for independence rather than the chi-square test for relationship. This is really the chi-square test for relationship. I'll say in a minute why it makes sense to call it chi-square test for relationship rather than chi-square test for independence. The alternative is that there is a relationship. You're not saying what it is, just saying there is a relationship between the two variables, which is the same thing as saying the two variables are not independent, which is the same thing as saying they're dependent. The reason it makes sense to call it a chi-square test for relationship rather than the chi-square test for independence is because you never prove independence. That's your null hypothesis, your H0, right? We never prove H0. We can only prove HA. So you can prove relationship, but you can't prove independence. So that's why it makes sense to call it a chi-square test for relationship. That's what you're really trying to prove here. The test is the same form as other tests. If the p-value is less than or equal to alpha, we're going to say HA is true. If the p-value is bigger than alpha, we've got our no conclusion. We can't say HA is true. So it's the same as we had with our regular hypothesis test. If the p-value is small enough, we can say HA is true. If the p-value is too big, bigger than alpha, we've got no conclusion. We can't say HA is true. The difference now is we're going to use different tables. We'll look at those when we get to them. We'll do an example and see how to use them. But you use the chi-square tables. The chi-square is a skew distribution. So it has a tail like this. So we use this table when we need to. And we're going to use chi-star, which is going to be like our Z1 we had earlier. So it's like Z1, it's using it kind of the same way. So it's like Z1. Not the same, but it's like Z1. So a chi-star, we don't have to worry about different cases, it's also the same thing. The chi-star is the sum, I just wrote out sum here rather than using the summation notation, the sum of observed values, those will be given to you, minus expected values, we'll see in a minute what those are, squared. So you can take observed minus expected squared over the expected and sum those up. And the expected values we're going to get from row and column total than the overall total. And they'll make more sense when you do an example. The expected values are going to be that you take the row total it's in, the column total from the column it's in, divided by the overall total. That's going to be the expected value. And that p-value here that we're going to get from the chi-square table is this thing here. So this we're going to get from the chi-square table. And chi-square is just a squiggly x, one with a square on top. So you get this from the chi-square table. And we need degrees of freedom here. So degrees of freedom is going to be number of rows minus 1 times number of columns minus 1. So chi-square, like the t, has degrees of freedom we have to worry about. But again, when we'll do a problem. Best way to do this is to do a problem, and then we'll see how to do this. It kind of makes more sense. So let's go ahead and go to a problem, and we'll come back up here and get the pieces we need. Okay, so here's a problem take home from the web problems. So it says the government wanted to see if the size of the family is related to their income. So those are our two variables, right? Size of family and income. And we want to see if they're related. They take a random sample, the government takes a random sample of 500 families and record their incomes. The results are given to you below. Test whether family size and income are related using alpha 0.01. So for you guys, to make things easier, I'll give you a table of the summarized results. Rather than just giving you the raw 500 values, I will break them up into groups for you, which will make things easier. So here, I'm going to put some totals on here. So what it's telling us is that here are two variables, right? Income is on this side, family size is up here. Those are our two variables. For family size, we were already about 3 groups. We broke into 3 groups. Those family sizes, those families with only 2 people, families with 3, then families with 4 or more. And for income, I've broken it up at 30,000. Those that make less than 30,000 as a family, those make more than 30,000 as a family. I'm going to erase this line, make it a little further out there. Make sure I get enough space. There we go, that's better. So what we see here, example, we see 52 families out of the 500 sampled, where there's 2 in the family and they earn less than 30,000. There's 94 with 2 in the family that earn more than 30,000. And otherwise, other ones, for example, there's 85 here, means that there are 85 families with 4 or more in the family, and that family earns more than 30,000. While here there are 77 families with 3 in the family who earn less than 30,000. So broken into these 6 groups. So what I need to do first is get my totals. So here, since these are the rows, right? This is the first row, second row. So over here, I'm going to have my row totals. And over here, these are columns, so I'll have column totals. So I'm going to add these up. So 52 plus 94 is 146, right? So that is my 52 plus 94. So that tells me there are 146 families out of the 500 with only 2 in the family. 77 plus 91 looks like, what, 168? So that is my 77 plus 91. So there's 168 families with only 3 in the family out of the 500 total. And here 101 plus 85 is easy, 186. So 101 plus 85. There are 186 families with 4 or more in the family out of the 500 sampled. And a quick check, the overall total, we know from the problem given, the overall total is 500, right? We're told there are 500 families. So a quick check. So let's do a quick check. 146 plus 168 plus 186. If you add that together, that is 500. 6 plus 8 plus 6 is what? Can we give us 12 plus 8 plus 20? 20 plus 180 is 200. 140 plus 160 is 300. 200 plus 300 is 500. So that's a quick check, and it seems to work here. So yeah, it's 500. And then get the row totals. So here I want 52. So here, because I put it below here, I want 52 plus 77 plus, come on, plus 101. Come on, 101. There we go. So that is 230. So there are 230 families out of the 500 making less than $30,000. And down here, I'm going to take my 94 plus my 91 plus 85. So that gives me a total of 270. So I have 270 families that make more than $30,000. Another quick check. 230 plus 270 is the overall total, is the 500, which is okay here, right? That works too. So the row totals and column totals must individually sum the overall total, which here is 500. So I've got my column totals, got my row totals. What I want to do now, and let me break this up so I can get a little more. That's what happened there, not sure what happened there. Oh, there's something weird there, so let me delete that. That did something weird, didn't it? Let's go back down to where you want. Try it again. So I'm going to break this up. So these values given, those are my observed values. Now I want to get, I'll put another one here, the expected values. Well, if you remember at the top, we're told the expected values you take the row total times the column total and divide by the overall total. So here I observed 52, but what do I expect? I expected 230 times, it's in the first column, so 146, divide by the overall total, which is 500. So I take its row totals in the first row, first column, column total, divide by 500. So let's calculate that. So I'm going to take 230 times 146, divide by 500, 67.16. So that equals, come on, equals 67.16. Likewise here, I put up an arrow here, so I don't have enough space there. I saw 77, I observed 77. What do I expect? Well, it's in the first row still, so it's going to be 230, right? But now it's in the second column. Second column, the column total is 168. Divide by 500. So I take 230 times 168, divide by 500. I get 77.28. That's my expected value. Now I can do that for the rest of them too. But one property of the expected values is they still must sum to these same totals, the same row and column totals. So they still must sum to the same values. So really, once you have one column left and one row left, you can find those by subtraction if you want to. So for example, this value here that goes in here, I got a couple ways I can find that. I could either do the formula, I could take the row total, which is the second row, so it's 270, times the column total, 146, divide by 500. Or I could just take, well, I know it must sum to 146 here, right? So I can take the 146 minus the 67.16. So I could, if I wanted, I could take 146 minus the 67.16. Either way should get me the same answer. So here's probably really easier with subtraction. 146 minus 67.16. Try it again. 146 minus 67.16. So 77.84. And you probably should check to make sure those are the same, but they will be the same. Probably good to not just take my word for it, try it yourself. So this one here got two ways. I got a couple ways to find it here, right, where the 91 is. I could take probably the easy way to do it is to take the 168 minus, come on, there we go, 77.28. Or I know I can take its row total, the 270, times its column total, now it's the second column, so it's 168, divided by 500. Either one should give me the same answer. Actually, it's even easier if you notice. Notice, since we've got two values, this is 77, this is 77.28, so if this is 91, it must be 91 minus the 0.28, or it should be 90.72. But you can do the calculation to make sure you get the same answer. So now here, where I observed 101, I got two ways to get it, right? I can either do the, I'll just do one of the ways here, but I got two ways. I can either do the regular way, which is take the first row, 230, but now it's in the third column, so that's times 186. Come on, 186. Divide by 500. Or I could take 230 minus 67.16 minus 77.28. Okay, either way works here. And that gives us 85.56. And now the last cell here, we got several ways of getting that, right? We can take the regular way, the row total, the 240, so we could take 247, 270 times the column total 186, divide by 500, or easy way is take the 186, the column total times the other value, the 85.56 up here. That's the easy one, right? Or we could take 270, the row total, minus the other two values in the row, the 78.84 and the 90.72. And that, either way we do it, we should get 100.44. So there's our table filled out. So now we've got all the values. We've got the observed values as one given to us. We've got the expected values. So now if we scroll back up, we can do the hypothesis test. We have the observed values. We have the expected values. We can find the chi-star, use that to get our p-value. So let's go ahead and write H0, write HA, write out chi-star, get the p-value, and do the test. So we're going to have to scroll down here, get some more space. Ooh, got some straight little marks here. Let's get rid of the straight marks first. Get rid of those. Okay, so null hypothesis we know as always, for this particular test, there is no relationship. So there is no relationship between two variables who are income and family size. The alternative, HA, is there is a relationship. I'm not saying what it is, but we're saying there is a relationship between family size and income, or income and family size. And we were using alpha was, I guess I'll have to scroll up quickly here. Alpha was actually in the test, alpha was 0.10, right? So alpha here, 10%, allowing out a 10% chance of being wrong. So our p-value, we know the p-value is just the chance the chi-square value is bigger than the chi-star value we get. And how do we get chi-star? Well, we are told chi-star, if you look at the formulas, with the sum of the observed values minus the expected values, I use OBS for observed, EXP for expected, squared over the expected, right? That's what we wanted. Sum of those things. So let's find our chi-star. So let's get a little more, let's go up and see the values again, see if we can get them in here. So what we're going to do here is we're going to take each pair. I'm going to take the observed 52 minus its expected, which is 67.16, square it, then divide by 67.16. Then plus the observed 77 minus the expected 77.28 divided by 77.28. I'm going to do that for all 6 of these cells here. Okay, so that's what I'm going to do down here. So it's kind of hard to get them both on the same thing, so I'll have to just kind of do it down here by itself. So we had, let's see, what was it? Oh, first, I guess I first need to write those down. So we had 52, 77, 101, 94, 91, and 85. And I've got the expected on my piece of paper, so I can write those down here. Okay, so we're going to have 52. The observed, the expected was 67.16. Going to square that. Let's see what I did there. Come on. I just moved it up a bit. There we go. Come on. Let's just erase it because I'm not sure what it's doing there. There we go. So 52, the observed, minus 67.16, the expected, divided by the expected 67.16. The next one, the observed was 77, the expected was 77.28, divided by the expected 77.28. The next one, the observed was 101, we expected 85.56, so we square that and divide by 85.56. The next one, we observed 94, we expected 78.84, square that divided by 78.84. So this gets a little tedious, but we're getting there. Got 2 more to go. Next one, we observed 91. We expected 90.72. We square that and divide by 90.72. And lastly, we observed 85. We expected 100.44. So we square that, then divide by 100.44. So that's our chi-star. We add those 6 things up. So what is chi-star? Well, if you add those up, you get about 3.422 is that first value. The next one is about 0.001, very small. Next one is about 2.786. The next one is about 2.915. The fifth one, the 91 minus the 90.72 squared, that thing is very small, 0.001. That's a 0 there. Let's make sure it looks like a 0. Let's make it more like a 0. 0. And then the last one is the 85 minus the 100.44 squared over 100.44 is 2.373. And if you add those up, we get chi star is 11.499, or approximately squiggly equals 11.5. Here we don't have to be too close because we're going to use tables, and the tables don't give us exact values, but approximate values. So the chi square is approximately 11.5. Okay, so at p-value up here, right, the p-value is the chance the chi-square value from the table is bigger than 11.5. Okay. So the last thing we need before we can use the tables, if you go back, remember we had a degrees of freedom. Degrees of freedom are the number of rows minus 1 times the number of columns minus 1. That's the degrees of freedom. So we need degrees of freedom here. So the degrees of freedom number of rows minus 1 times the number of columns minus 1. That is the original rows and columns. So note, originally we had what, 3 columns, 1, 2, 3, family size of 2, 3, and 4 larger, and 2 rows, less than 30,000 or more than 30,000. So it's going to be 2 minus 1 times 3 minus 1. Or the degrees of freedom here is just 1 times 2, or 2. So why is it 2? Well, actually, if you go back to the original table, it makes sense. Remember, once we'd found these first two, the 67.16 and the 77.28, the other expected values we could find by subtraction, because they had to sum to the same totals. So notice, once you find everything, all the expected values except those in the last column and the last row, those ones you can find by subtraction. That's why it's called degrees of freedom. Because here, once I found the first two values, the first two expected values, I could find the rest by subtraction. I didn't need to use the formula. So they weren't free anymore. They weren't free to roam around. They were fixed numbers. I just didn't know what they were yet. That's what degrees of freedom is kind of telling us. So degrees of freedom is number of rows, the original rows, not the extra ones you add. Number of original rows minus 1 times number of original columns minus 1. Or remember, number of rows, number of columns are the number of categories you have for your variables. So it's the number of categories minus 1 for each of your two variables. You multiply those together. Okay, so now we need the chi-square table. So here's the chi-square table. So notice with the chi-square table, let's get the highlighter here. First thing you do is look for degrees of freedom. Well, that degrees of freedom is 2, right? So look for 2. And now what I want to do is I want to look across for that 2 degrees of freedom. See how straight I can draw here? Not very. Woo! Up and down, up and down, up and down. There's the 2 degrees of freedom, kind of. I want to look at that 2 degrees of freedom. There we go. And kind of look for where our value falls. So here, our value falls between here, right? Our chi star was about 11.5, 11.499. It falls between these two, 10.57 and 11.93. So that means if you look up at the top, our p-value is going to fall between these two numbers. So it tells us here our p-value is somewhere between. Here be a little careful. Notice the chi-star values get bigger, right? 10.597, 11.983, 12 point, they get bigger. But these values, these alpha values on the top get smaller, 0.25, 0.2, 0.1. So actually you have to switch the order. So it's between 0.0025 and 0.005. Falls between those two. So that's what, so don't get an exact p-value, get a range. It falls somewhere between those two values. So it's between 0.0025 and 0.005, because our chi-star value fell between those two numbers in the chi-square table under 2 degrees of freedom. Okay, so we're going to get the p-value here. So our p-value, we said it was between 0.005 and 0.0025. Right, that's the range it fell between. Well, notice our alpha was 10%, right? 0.01. So 0.10, 10%. So obviously we're lower than that, right? We're way below that. We're less than 0.5% here, between 0.5% and 0.25%, 0.0025, 0.005. That's actually another way to kind of do the chi-square test. If we go back to the table, another way to do it is to say, well, where is our alpha? Notice here our alpha was 10%. And ask kind of what side of the alpha do you fall on? If you're on the upper side of alpha, then the p-value is less than or equal to alpha. That's where we were. We're up here. But if you're over here, the p-value is bigger than alpha. So here we're on the upper side of alpha, so actually the p-value is less than alpha, because maybe the alpha values get smaller as they go across. So here, our p-value is less than alpha. Less than or equal to alpha. So we can conclude HA, right? Just like a regular hypothesis test, you can conclude HA. And what is HA? HA is that the two variables are related. So you can conclude HA. So you can conclude that income and family size are related. They have a relationship. So the last step is, if you say they are related, how are they related? So now down here, guess I have to again erase these extra little marks here. Come on. Get rid of these little marks so we can get right what the relationship it is. There we go. Get rid of some of those. So how are they related? Ooh, how are they? That's pretty ugly. Let's try again. How are they related? So what you do is you go back to your data and you look where the observed is a lot bigger than the expected. Actually, I'll write that down. When we go back to the other part, I'll write that down there. You look where the observed is bigger than the expected. So here, here I observed 94. I only expected about 79, 78.84. These two are very similar, right? Here is slightly bigger, 91 versus 90.72, not a huge difference. But here we observed 101, but we only expected about 85.5. So what you do, let me go back here again, how are they related? You look where the observed is quite a bit bigger than the expected. That's going to give the relationship. So here, what we saw was, again, scroll one last time here, more small families between two in the families, earning more than expected in this higher group, $30,000, higher than $30,000, right? While we saw the large families, 4 or more, earning less than expected, more of them down in the $30,000 than we expected. So that's the relationship. So let's go ahead and write that. Again, I guess I'll get rid of some of these extra marks, get more space here. There we go. So we saw small families right, those with 2 in the family with a size equal to 2, earning more than expected. And large families, in this case the size was 4 or more, earning less than expected. You saw more of them in that lower income. That's the relationship it appears to be. Here, since both variables are really quantitative, right, they're really, both size is quantitative, it's integer values, income is dollars, it's quantitative. You could talk about association. You don't have to, but you can only do that if both variables are quantitative, and here they really are. So here, notice it's sort of a negative association. Small with big, big with small. Small families, big income, big families, small income. But you don't have to say that, but you can if both variables are quantitative. If they're not quantitative, like political affiliation or sex, you can't do that. But here we could. So that is the conclusion for this particular problem. We conclude that HA is true at p-value small enough, it's less than alpha. We had less than a 0.5% chance being wrong up here, between 1/4 and 1/2, without up to 10% chance being wrong. We say they're related, then we go back and look where the observed is bigger than expected. Where the observed is bigger than expected, that's the relationship. So we saw small families earning more, larger families earning less. The last thing I mentioned before we leave, because you're probably maybe thinking about it right now, why are they called expected values? So let's finish with that. So this is another problem itself. It's just an end note here. Why are they called expected values? Well, expected values are what we expect to see if the null hypothesis H0 is true. So no relationship between the two variables. That's why they're called expected values. They're what you expect to see if H0 is true if there's no relationship. So what it's telling us, if you go back to the table, here it's saying, if there's no relationship between family size and income, I expect about 67 families in this first group, where I saw 52. I expect about 79 in this group down here. I expect about 77 here, which is close to what we saw. I expect about 91 here, again, which is close to what we saw. We expect about 85.5 in here, which is way lower than we saw. And we expect about 100.5 in here, which is way more than we saw. But that's why they're called expected values. And that is why the chi-star value compares those two. The chi-star value in the hypothesis test is seeing how far are the observed and expected. If the observed and expected are far apart, then we get a big chi-star value. And a big chi-star value will tell us, aha, HA is true. There's a relationship. Because the observed and expected are far apart. But if the observed and expected are close together, then maybe H0 is true. So if the observed and expected are close together, the chi-star will be small. A small chi-star means a big p-value, so we can't say HA is true, got no conclusion. Maybe they're related, maybe they're not. But that's kind of what this chi-star is doing, is looking at the observed and expected. The further distance between the observed and expected, the more likely HA is true, that there's a relationship. The closer the observed and expected, well, the more likely there could be no relationship. H0 could be true. That's what we're doing here. That's kind of what this chi-star is measuring here. Okay, so let's go ahead and stop here, and we'll do some more examples next time.